formulation of advanced processes for excellent properties. And
I think it will be the truly encouragement, inspiration for me to continue my research work as a national scientist in National Metallurgical Laboratory Jamshedpur, so that the technology and research which is being developed throughout my journey, it will be utilized in the society, in the industry. And also I express my gratitude for such a very nice felicitation for this award. And so in this NM Sampath Award lecture, I am going to discuss on the topic having the title of Advancement of Coating Technologies, which are being developed last 8 years as a scientist, as a journey in National Metallurgical Laboratory. And I'm going to focus some of the few technologies which I developed with a new approach compared to the conventional practices which are being used in the industries, and which is a need of the future, I think. So these are the list of the technology developed under the different sponsored projects, collaborative project with the industries, the funded by the CSR organization, then DST, Ministry of the Steels. And out of this technology, I'm going to focus these 5 different technologies which are developed with the new approach. In the first approach, I'm talking about the mitigation of the galvanizability issue which is facing by most of the steel industries in a continuous galvanizing line plant, that for the advanced hosting steel sheets. And this approach, the different industrial practices with the application of the iron-based sol gel pre-coating, it can mitigate, and I think this will be the energy incentive and also the less economical. In the second technology, I'm talking about the galvannealing coating, which will give the better combination of the super hydrophobicity, adhesion and the corrosion performance. So that the need of the further secondary treatment, the chemical additional treatment, as well as application of any organic paints, only for to get the construct the super hydrophobicity on this galvanizing and the galvannealing coatings, how we can get within the one single galvannealing process itself with the help of the in situ generation of the intermetallic layers. In the third technology, I am going to talk about the existing issue for development of the zinc aluminum magnesium coating, which is actually the future technology in the galvanizing process, which will give the 10 times superior corrosion resistance compared to the conventional GI. And the fourth one is very interesting, is that most of the time we apply the organic paints for the aesthetic application on the galvanizing and galvannealing coating, just for the protection and for the different shades of the colors. So the idea is that can we develop the colorized galvanizing coating during galvanization process itself. And in the fifth approach, I'm talking about the electrodeposition coating, which is developed for the zinc roll. So it will improve the online life cycle during the galvanizing process itself. So specifically talking about today's lecture, I'm going to discuss the particular hot dip galvanization as well as electrodeposition process, and how I can approach with the new thinking, so that it not only the research point of view, but it should also be applicable for the industry and viable to the industry. So in the first, I'm talking about mitigation of the galvanizability issue of DP980 steel, that is the advanced casting steel grade, with the help of the innovative iron-based sol deep pre-layer. So this is a schematic of the industrial continuous galvanizing line. As we know that the advanced casting steel sheets, which is in the large demand because of the high tensile strength and the ductility, and as well as its application in the structural and the automotive for the car bodies, it gives the immense requirement of the corrosion protection because of the very small thickness of the steel sheets. And right now the practices are that different galvanizing coatings are being applied, but the main issue for these advanced casting steel sheet is that most of the future point of view, the developed advanced high strength steels, they have very poor galvanizability. So the idea of this development of this technology is that can we develop the any application of the pre-layer just before galvanizing, so we will get the good quality of the coating. So this is a schematic of industrial continuous galvanizing line in which the steel sheet after the cold rolling, it is a process for the annealing treatment, so we will get the optimized microstructure, and then it is a dip into the molten metal bath to get the galvanizing coating. But the main issue is that during annealing treatment, the alloying element which are the present, which are added for the microstructural point of view, they causes the formation of the surface selective segregation and the oxidation, and they form the tiny islands of the oxides, and because of that it hampers the reactive reaction of the molten zinc on the steel surface and causes the uncoated spots. The different industrial practices are being used to mitigate this problem, which include the post pickling treatment, control annealing treatment with a controlled dew point, application of the pre-layer using the electrodeposition method such as iron, copper, nickel, and application of the simultaneous oxidation reduction process, and addition of the active alloying elements. But all these processes, they are applicable for particular grade of the steels and particular composition of the galvanizing bath. So idea is that can we develop a process, a single process which will not need any change in any process, which will not require any change in the process parameter in a continuous galvanizing line, and we will get the good galvanizability. So the idea is that in this hot dip galvanizing, modified hot dip galvanizing process, this mitigation problem can be used with the application of this iron based pre-layer, sole dip pre-layer, just before annealing treatment on the steel sheets, so that this iron based pre-layer will be reduced, cured and reduced during the conventional annealing atmosphere, which is being used in the continuous galvanizing line of the nitrogen and the hydrogen, that is the reduction atmosphere, and so we will get the metallic thin layer just before dipping into the molten metal bath. And this metallic Fe layer, it will improve the reactivity of the molten metal zinc on the steel surface, and we will get the uniform coating without any uncoated spots. So for this, the iron based salt solution we have prepared using the iron salt precursor, and we and the effective precursor to the solvent ratio were optimized to get the uniform salt dip pre-layer, and then further the steel sheet which is coated with the salt dip pre-layer, it is further simulated for continuous galvanizing process in a hot dip process simulator, which is a very unique facility at the CSIR-NML. And then optimizing the 400 nanometer, the sole dip pre-layer, and optimizing the dew point around minus 30 degrees Celsius, that enhance the good galvanizability of DP980 steel, and further characterization of the coating. When we compared, when we done the comparative analysis for the conventional galvanizing coating as well as the modified galvanizing coating, it showed very fine spangles on the galvanizing coating and the very fine, very less surface roughness. And when we carried out the cross-sectional analysis, where we confirmed that the formation of the inhibition layer, that is actually the important key factor for the good adhesive strength of the galvanizing coating on the steel surface, which is very important during the further forming operations for structural and the automotive application. And the formation of this very uniform dense inhibition layer of Fe2Al5, which actually the indication of the separation of the surface selective oxidation and the segregation of the alloying element on the DP980 steel, and getting the uniform inhibition layer and getting the and suppressing the main issue of the formation of the uncoated spot during galvanizing process. So further its mechanical testing and the powdering resistance testing, it showed the inherent characteristic of the good adhesiveness. And in corrosion performance, this modified coating, it also showed the it actually sustained its inherent sacrificial cathodic corrosion protection ability, considering if you see the potential difference of the steel and this is a galvanizing coating, so it is quite more than the minus 100 millivolt. So it gives the indication that the modified galvanizing coating will give the sacrificial cathodic corrosion protection, as well as if you talk about the corrosion property from the Tafel polarization test, it gives a very unique property that the corrosion of the galvanizing coating is mainly controlled by the cathodic reduction process, and also when we conducted the salt spray test, it actually extended its corrosion life from 160 hours to the 432 hours. So this is the interesting improvement in the corrosion resistance for the modified galvanizing coating. It is mainly due to the formation of the spangles or the overlay spangles on the coating in a more the HCP highest the texture coefficient, and which increase actually the resistance to the polarization. And the second reason for improvement in the corrosion performance is that if you talk about the protective corrosion product, which is mainly form of the cement collide, which further protect the galvanizing coating underneath of the galvanizing coating, and the large extent of formation of this product, which improved the corrosion performance and the corrosion resistance of the galvanizing coating. So in a further, with respect to the time evolution, we studied this coating, and it showed the very significant improvement in the resistance to the polarization. So with respect to the time performance, it showed the good performance, so it indicates the good application for the structural and the automotive. So we also further scale up this technology from the small scoop on to the large size of the steel spangles of DP980 steel of 22 by 11 centimeter, and it showed very good mitigation of this galvanizability issue. And this is a summary of this. So application of the iron solely pre-layer around 400 nanometer just before annealing treatment, it suppressed the surface selective segregation and the oxidation of the alloying elements, and it improved its galvanizability. So in the second technology, I am talking about the galva annealing coating. So just I'll introduce that. After the galvanizing, if we talk about the galvanizing coating, it has very poor pentability and the weldability. Therefore, after coming out these steel sheets, that is the galvanized coated steel sheets, it is further subjected for the post annealing treatment, that is called as the galva annealing. So during galva annealing, the interdiffusion of the Fe and the zinc, Fe from the steel and the zinc from the zinc coating, it takes place, and the different intermetallic layers of the gamma, delta, zeta, eta, they are formed within the coating. But among these intermetallic layers, the important layer is the delta layer, which contains the Fe around 7 to the 12%, and which is considered as the best combination of the mechanical as well as the corrosion properties. But optimizing this delta layer, it causes the formation of the thin gamma layer, which is very brittle, and while optimizing this delta layer, it is very means increasing the delta layer thickness, the effective thickness of this gamma layer also increases, and that is very detrimental during the forming operation. So the spalling of the coating, it can take place. So that and also the second approach and the second thing is that these most of the GA and the GA coating are further subjected for the additional chemical treatment, and also it is applied with the organic secondary layers like paints or any polymer coatings. So it will enhance its super hydrophobicity, and also the other aesthetic applications, the barrier, additional barrier for these GA and the GA coatings. So but in this new approach is that can we develop all the combination of this super hydrophobicity, optimizing of the delta layer, good adhesion and the corrosion resistance within a single galva annealing process itself. So with the help of the addition of the titanium as an alloying element, we achieved this all the combination of the properties within the galva annealing coating itself. And if we compare the development of these coatings in a microstructural point of view, here we can see the conventional spangles of the zinc which are formed in the galvanizing coating. The GA coating, it showed the formation of the eta overlay, and addition of the titanium in the bath it start to form the intermetallic layers within the coating. So that means the reactivity of because of the addition of the titanium of the zinc bath, it improved, and because of that the delta layer nucleation takes place within the galvanizing coating itself, which is generally takes place in a galva annealing process, right? So further galva annealing treatment, we selectively improved the formation of the T type of the phase on the surface of the coating, and because of this T type of the phase which are formed on the surface, it actually improved its super hydrophobicity. So this is a cross-sectional analysis. Here we can see the formation of the conventional intermetallic layer, inhibition layer and remaining the overlay of the eta phase. In a GA coating, the different layers are the formed, but if we talk about the delta percentage is very less. Addition of the titanium in the bath, in a galvanizing process itself, it start to nucleate here the T and the delta phase. And if we do the controlled annealing, then the formation of these gamma 1, delta and the T layer, it actually gave the good combination of the adhesion strength as well as the corrosion properties and the super hydrophobicity. So super hydrophobicity is mainly ascribed to because of formation of the T phases on the surface. So the surface roughness is improved, and because of that, the super hydrophobicity interestingly improved from this 44.2 to 148. That is nearly super hydrophobic approach, and also the durability of this super hydrophobicity were further checked with a cyclic corrosion exposure, and in that case there is a merely reduction in the water contact angle, which actually hardly took place around 135. So it is around some hydrophobicity. So during the corrosion itself, because of the formation of the T layer, it is so corrosion resistance, it will also sustain its super hydrophobicity. In adhesion test and the nano indentation test, separately we check all the hardness of the intermetallic layers, and there is a quite reduction compared to this gamma layer because of the formation of the gamma 1. So the cause of this brittleness of this galvanizing, it is also improved in this modified galvanizing coating. In a corrosion performance analysis also, the coating, it showed the sacrificial cathodic corrosion ability, which is actually the main inherent property of any galvanizing coating. In corrosion test also, it showed the good corrosion resistance in a Tafel polarization, and in a salt spray test, it improved the corrosion resistance from 168 hours to the 622 hours. So interestingly, again, this is because of the formation of the large content of the T phases as well as the Simon colloid product on the corrosion. In a EIS analysis, the resistance to the polarization increase, and the formation of the protective corrosion product and the T layer, it actually caused the barrier for penetration of the corrosive species such as the Cl- ions. So summarily, addition of the titanium within the galvanizing bath, we can obtain the better combination of the super hydrophobicity, adhesion and the corrosion resistance within a galvanizing coating process. So there is no need of any additional chemical treatment or any application of the organic pre-layers. So in a third coating, I am talking about the advanced zinc aluminum magnesium coating. So if you talk about, because of this alloying element of aluminum, the magnesium, it improves the corrosion resistance of conventional galvanizing coating around 10 times. And if you talk, but main issue is that we cannot increase the aluminum and the magnesium to a large extent because of formation of the additional the brittle phases. And among these brittle phases, the formation of these the primary MgZn2 phase, which is like in the hexagonal shape, it is much more brittle, and because of their brittleness, when it is subjected for any forming process, the cracking takes place, and because of this poor crack resistance, the powdering takes place during the forming operation, and that affects the die and the punch. And also we can see here the crack which is propagated from top surface to the coating substrate interface. So this is further affect it can cause the spalling of the coating as well as the hamper the corrosion resistance applicability of this galvanizing coating. So the idea is that addition of the controlled composition of the aluminum, addition of the nickel alloying element, and the combination of the effective cooling rate, we can suppress the formation of the surface constituent phases in the zinc, aluminum and the magnesium coating. And all these processes were simulated in our SDPS or D process simulator. So this is a conventional zinc, aluminum, magnesium alloy coating, which mainly contains the MgZn2 phase in both phases, in both form like hexagonal, as well as if we see that around the hexagonal shape there are the formation of this binary eutectic of zinc MgZn2 phase, which is also more brittle. But if we compare the remaining matrix, it is of the tertiary, it is of the ternary eutectic of zinc, aluminum and MgZn2 laminates. So the approach is that how we can suppress the size of this MgZn2 phase, or how we can evolve this MgZn2 phase with the addition of the nickel and the effective cooling rate, and how we can increase the quantity of the ternary eutectic phase within the coating, so that we can improve the cracking resistance as well as the corrosion resistance. So because of this addition of this nickel alloying element and increasing the aluminum content up to 10 weight%, so combination of this, it will cause the evolution of this hexagonal to the petal-like structure, in which the core of this MgZn2 phase, it is an enrich of the zinc and the aluminum because of the spinodal decomposition, which takes place during the cooling of the coating around 277 degrees Celsius. And around it, the MgZn2 phase, the growth of the MgZn2 phase takes place. And here in the cross-sectional analysis also, we can see that the nucleation of the MgZn2 phase from the substrate coating interface towards the surface, it is also minimized in this optimized coating structure. In a cross-sectional analysis, the effective role of the nickel is that the initial formation of the inhibition layer, which forms between the coating and the substrate, and it actually causes the refinement and the formation of the tiny crystals of the Fe2Al5, and it further actually cause to form is further cause to any growth during the galvanizing process. So we got very good thin and the uniform inhibition layer. So that is an important role of the nickel, and because of the inhibition, the remaining solidification of the coating which takes place, which act as a nucleation point, heterogeneous nucleation, and because of this heterogeneous nucleation ability, we suppress to the nucleation and the large growth of the MgZn2, whereas we try to capture the zinc and the aluminum, the alloy combination, which is actually the primary phase, and which actually cause for nucleation of the MgZn2. That's why we got the core of the MgZn2. So the main important role of the nickel is that the evolution of the MgZn2 phase. So in a further characterization of this microstructural, the size of the MgZn2 is decreased, the width of the lamella, it became very thin, and also the surface roughness is reduced. If we talk about the conventional, it is very high surface roughness because of this formation of these surface constituent phases of MgZn2, which is of the large lathe and the hexagonal shape, where we find out that very refinement of the structure obtained with the combination of the nickel and the higher aluminum percent, around some 10 weight%. So in a further powdering resistance test, it showed very good resistance, and the crack density also reduced significantly, and because of these hardness of this MgZn2 phase, because of the formation of the core zinc aluminum enrichment, it reduced, and also the increase in the lenticular structure of the lamellar of the lamellas of the ternary eutectic phase, it further actually act as a crack. It also prevented the crack propagation during the bending test. So in a corrosion performance, the coating showed very good performance. It extended the life cycle from around 2000 hours to the 4000 hours, and this is mainly because of if you talk about the cross-sectional analysis of the corrosion product, there are the formation of the double layers. In the top layer, that is a flocculent type of the cement colloid product were formed, and underneath that, the LDS type of the corrosion, that is layer double hydroxide of the zinc and the aluminum were formed, and because of this, it further actually protected the underneath zinc, aluminum and magnesium coating, and that's why it showed the improvement in the performance during salt spray test. So in a summary, addition of the nickel alloying element, we can improve, you can increase the content of the aluminum up to 10 weight%, and we can evolve the MgZn2 phase so that it can be applicable for the good corrosion resistance and the good cracking resistance as well as the corrosion resistance. So this is a fourth new approach. As we know that till now I have discussed all the galvanizing galvannealing coating, which shows generally the silver appearance, right? Most of the galvanizing coating are of the silver appearance, and in general the steel substrate after the galvanizing, they are passed to the different chemical treatment, chromatizing, phosphatizing, and then for aesthetic application, different color shades, the paints and the organic layers are applied. But the idea is that can we develop the galvanizing coating, that colorized galvanizing coating within dipping process itself, so it will avoid the further any additional surface treatment, any chemical treatment, as well as application of any organic paints for the aesthetic application. So we developed this technology for, it is applicable for both type of the galvanizing process. One is the continuous galvanizing line where the steel sheet and the wires they are produced, whereas in the batch type of the process, the pillars, then towers, then angles, and also the small size of the component which are being used for structure and the automotive applications, they can be colorized with the optimized bath composition, bath condition, and the process parameter only. So just if we control these bath conditions, we can obtain these different colors, different shades of the colors within a single dip only. So no need of application of any further treatment, the post treatment. And this process we develop for the sheet, steel sheet as well as the wires. And the main mechanism for getting the color is because of the addition of the alloying element. When it comes from the bath, it forms the thin layer of the oxides, and because of the total internal reflection and the interference of the light, depending on the thickness of the thin film of oxide film, we can get the different shades of the colors. So just by changing the composition and just by controlling the temperature, we can obtain the different shades of. So no need of any additional treatment, and it is applicable for batch type as well as the CGL line. So in other process also we got the good this. At the last this is the last one technology, that is electrodeposition of the chromium carbide coating on the zinc roll for continuous galvanizing line. I'll just give the brief. This zinc roll, it is completely submerged in the galvanizing bath, and actually it acts as a guide for the steel sheet which is moving at very high speed. And application of this chromium carbide coating, it improved its life cycle. This completely submerged zinc roll, there is a continuous dissolution of the Fe takes place within the bath because of the reaction of the zinc. It not only forms the large dross on the surface of the bath, but it also hampers the quality of the coating. So therefore the different approaches are being used. But if we talk about the present one, that is a chromium carbide cobalt coating, which is a thermally spread around 500 micrometer thickness on the zinc roll, but it gives extend the life cycle from 4 days to up to only 10 days. So the approach is that can we double this life cycle of the zinc roll by using the electrodeposition of the chromium carbide coating. So we studied this coating for the prototype of the zinc roll at laboratory by using this customized rotary electrodeposition system, and here we increase the life around 23 days. So that is more than the conventional thermal spray coated zinc rolls. So this is a summary of all the 5 different technologies. We have done the we have actually done the research on the different coating technologies, sol gel coating, electrodeposition coating, and I am giving the example of particularly hot dip galvanizing coatings, in which we actually approach in a different way, so that our research will not be constrained only for getting the new science, but also it should be the applicable at the industrial level. So these are the 5 technologies, and right now these are all the approved by our CSR NML for commercialization, and the plant trial of this coating will be in the future. So these technologies I have developed within last 5 years, and just my point is that when we approach any research, the first thing is that what exactly its application, what is the existent process, and how you can improve this process. But at the point we will have to think that we cannot do the random changes or random the change in the process parameter, so it will not be useful at the industry. So we optimized this research in such way that all these technologies will be viable at the plant level, so it will be the beneficial for the large industries as well as the MSME industries. Thank you.
Yeah, thank you, Dr. Mahesh. And then he was talking about very good presentation. You are talking about the incremental innovations, so that it can be directly adaptable by industry without major changes. One is that novel pre-layered galvanic, and then there is galvan annealing process, and then And also colored, that's also very good effects. We're also eliminating the paint and then other things, and then all these processes. And then in fact, this bromine carbide coating also improving the significant life of the road.
Right.
It can be directly adaptable by the technology. So once again, we can give him a big hand for his presentation, which can be easily adaptable by industry.
Right.
Thank you very much.
Thank you so much.
For the wonderful organization and for having all of us here. Now in today's talk, I will share a concept which I would say high school level chemistry, which can perhaps help us make the layered transition metal oxide cathode materials a little better than what they are today. So before we go on to the details, just wanted to give the Indian battery research scenario across the country, and so I have listed only the institutions and the national labs here, not the industries. But then we can see that it's like widespread from north to south and east to west. So there are a lot of activities. And many places have been missed out in this slide, probably because of my ignorance, and also because I could not fit in anymore in the slide, which is a very good scenario. So I'm happy that it's very difficult to fit in anymore, though there are many more institutes who are working on battery and really allied areas. So in IIT Bombay, in my group, we work a lot on the sodium ion chemistry. Of course, we still do lithium ion chemistry and also a little bit of solid state chemistry. Now coming to IIT Bombay, so we have quite a few groups working on various aspects related to batteries. So battery chemistry, then there are a lot of people who are working, lot of groups who are working on the electrode level and cell level simulations and optimizations, including cell life predictions and electrode level engineering, which are very important. Then there are groups which are working on the aqueous chemistries, the flow and the air batteries. We also have groups working on the recycling aspects, and also groups which can take our cells and make good battery packs out of them. And coming to the facilities, we have the lab scale facilities. This is just a picture from my lab. And we also have a pilot scale prototyping facilities, which many industries use at IIT Bombay. And okay, so a brief about me, but that's not needed now. Right, so the reason we would like to work on batteries and develop batteries which can be, let me not use the word less expensive, I don't like that word, but which can be more sustainable and which can help the common people of the country a lot, and which can help India become self-reliant on the battery technology. And that is the theme of the meeting today. So self-reliance on battery technology. So we still have a lot of places where we have power outages even today, and so we need batteries for good grid scale energy storage and also other forms of stationary storage. And also we are very much aware of this, some of our cities, so they suffer badly because of environment pollution. So we need batteries to make the electric vehicles, and not the electric vehicles which can be only used by a few elite people, but we want the electric vehicles to be used by people like us who are the common people of the country. So that's very important to address all these problems, and that's where probably sodium ion battery is important, especially in the Indian scenario. Now, sodium ion battery is the chemistry looks pretty much similar to the lithium ion battery chemistry, but there are a lot of differences when we look into the details and smaller the aspects, the scientific aspects. So anyway, overall, so the good thing about sodium ion battery is that it can really make it can really help with reducing the import dependencies of our country when I compare it with the lithium ion battery technology. And as we know, sodium ion batteries, cathode materials don't need cobalt. We can make the layered transition metal oxides, some of which I will show today, but we don't have any cobalt in that. Also, current collector, we don't need copper. We can have aluminum both sides, which is good for the cost-related aspects. But it should not be just the cost which makes technology important. There should be some benefits in terms of its performance and safety aspects as well, and that is where also sodium ion battery scores over lithium ion batteries in some of the aspects. So it can be a little more safer than the lithium ion batteries, and it can be used over a wider temperature range from Ladakh to Kanyakumari. It can cover the entire temperature range. And also when it comes to fast charging, sodium ion batteries are a bit more capable to take up fast charging than lithium ion batteries. Something which was not thought about earlier, but it is true. But then, of course, it's an upcoming technology, and also even with lithium-ion technology, which is so well matured, there are still some problems which we need to address and keep on doing them, and also lead to further improvements. But sodium-ion batteries definitely have a lot of issues which need to be addressed, and that's why people like us who are interested in doing some research are useful. Otherwise, we would have lost our jobs and nothing to do, right? So right from the anode side, which cannot use graphitic carbon, which has been the workhorse anode for lithium-ion battery, to the cathode materials, and especially which we need for high capacity and energy density, there are problems which need to be addressed. And also electrolytes, we don't know which is a good electrolyte for the sodium-ion battery, at which upper cutoff voltage, etc. So that also needs a lot of development and understanding. Now, having said that, and being a researcher focusing a lot on the sodium-ion batteries, there is one question which always comes up. Can we have sodium-ion batteries which have energy density higher than the LFP lithium-ion chemistry? And I really don't like that question, and there is a reason for that. And the history of evolution of the battery chemistries, of course, starting with lithium-ion, not going further back. So if we look at the evolution of the battery chemistries and the market they took up, tells a very interesting story. See, late 1990s and the early 2000s, we had the lithium-ion technology coming up, the first generation and the maybe second generation lithium-ion batteries. The market they took up were the consumer electronics, and they still have the lithium cobalt oxide based cells. Maybe instead of 100% graphite, they maybe have some sprinkling of silicon, but they're still lithium cobalt oxide based. Now, when the NMC lithium-ion batteries came up, they did not take up the consumer electronics market, which still has the lithium cobalt oxide based cells. But they opened a completely new sector, the electric vehicles, the high-end electric vehicles, the very high-end electric vehicles for us, and the e-aviation. And the market size increased, as one can see. Then comes the LFP lithium-ion batteries. They did not take up this sector. The NMC batteries have been used and will be used in these sectors, but rather they came up with a new market, the relatively low-cost EVs. So this is a slide from Darren in the United States. So what he says, low-cost EV may not be a low-cost EV for us. So that's why I use the term relative low-cost EV. And also some stationary storage. And the market size is even bigger, but it did not take up these two markets. Now, sodium-ion battery, does it need to compete with the LFP lithium-ion battery? Probably not, because it can generate its own market and maybe have a even bigger market size. It can lead to even low-cost EVs, which may be really low-cost and affordable by us, the three-wheelers, which some of these countries may not be bothered about. It can open up a huge list of other markets which the lithium-ion batteries have not yet opened up. So there is a huge scope in terms when it comes to sodium-ion battery technology, and we don't really need to compare it with the LFP lithium-ion battery technology. That's my viewpoint. Now, coming to the chemistry, and the cathode materials, yes, for any battery technology, and especially the upcoming one, we need to go higher and higher up the energy density. So what do we need to go up in the energy density scale? We need to have cathode materials which can give us higher capacity. And if we look at this, it is the layered sodium transition metal oxides which can lead to higher and higher capacities. Again, I don't want to use the term more than or less than LFP, but higher and higher energy density. So that's why the layered sodium transition metal oxide as a class of cathode material is very important for the sodium-ion battery chemistry. So now, what are the layered sodium transition metal oxides? It's actually very interesting from a material scientist's point of view. It is a wonderful structure, and it can take up more than one type of structure. See, lithium cobalt oxide or the lithium NMCs, they adopt one structure. That's the lithium transition metal oxide, the layered lithium transition metal oxide, because in that the lithium can take up only octahedral side and not prismatic side. So the lithium cobalt oxide and a lot of the layered sodium transition metal oxides take up this O-type structure with the lithium ions in the octahedral side and the oxygen ions arranged as ABC, giving this three. Now, with sodium ion being a little bigger in size and lesser surface charge density, they can also take up a prismatic coordination, which is fantastic. because a prismatic coordination leads to faster sodium transport, and that is one of the reasons why sodium-ion batteries are probably better suited for fast charging on the cathode side, not coming to the anode side. There are problems with fast charging on both sides, but yeah, so sodium ions can take up a prismatic coordination, and we can have this kind of a structure, a p-type structure. Again, this too comes from BaAb of the oxygen ions. Now, so this is excellent in terms of the rate capability, but the p-type structure has a big problem. It can form stable structure only with a sodium content of 0.7 per formula unit or below, which is a disaster, because for alkali metal ion cells like lithium and sodium ion, the cathode material is the reservoir of the alkali metal ion. So we want the p-type structure with a sodium content of 1 per formula unit. Probably not possible, but we can try to go closer to 1 per formula unit and go beyond 0.7 per formula unit. Now, all these layered transition metal oxides, they have one big common problem, that is they are highly hygroscopic. If we leave it on this table, leave it for a few minutes, they are totally gone. They cannot be used to make a cell. They cannot work as a good cathode material, and they may not even actually work as a cathode material. You won't get any capacity out of it, because the starting point of this degradation is that the sodium in the structure, it comes out. It spontaneously gets desodiated. And the greater sodium transport kinetics is partly to do with that. So the sodium comes out, it gets replaced by H plus or H3O plus from the atmospheric moisture or water, and so there is a sodium H plus exchange, Na plus H plus exchange. That is the starting point of the degradation. Now once sodium starts coming out, it will react with the other things present in the moisture, water vapor, carbon dioxide, from lot of surface species which are disastrous for a battery performance, and also the structure will not remain stable because sodium is coming out. Okay. So that's a big problem. So that needs to be addressed. Now, if it is so unstable when exposed to the air, one cannot even think and put it in a water to make an electrode slurry. That's kind of like impossible. So improving the air-water stability is a very important aspect to use the layered sodium transition metal oxides at a larger scale, where there will be some exposure to air at some point of time, even if we don't want to, even if we neglect the usage of an aqua slurry. So this slide summarizes some of the problems. One of them is the multiple phase transformations during desodiation, sodiation, that is charging, discharging, and capacity fade, which one can address by composition changes and also structural changes associated with that. Then Young-Taylor distortion, if we have a Young-Taylor active ion. Then transition metal dissolution. Well, these are there even for the lithium transition metal oxide cathode materials. And if we go through Jeff Dunn's work, the transition metal ion dissolution is a big problem even in lithium iron phosphate, especially at high temperature, and it's a disaster for LMFP, the iron and manganese ion dissolution, which nobody thought about before. Now, because they are so highly hygroscopic, we cannot even think of using a water-based slurry to make electrodes out of this layered sodium transition metal oxide. So this is the scenario in general. Now, if we look at this, so what can we do to try and address this? Now, if we look at the structure of the layered sodium transition metal oxide, I will come back to this point again. So it's beautiful in the sense that it is the same oxygen ion which on one side is bonded to a sodium ion, making a highly ionic bonding, and on the other side the same oxygen ion is bonded to a transition metal ion, making an ionocovalent bond. So why am I saying this? That is because from our high school chemistry we know that the strength and the length of a ionic bond is totally dependent on the electrostatic attraction. So we cannot do anything. When it is oxygen ion, when it is sodium ion, it will be dictated by the electrostatic attraction. We may not be able to do anything. No, but in this structure, it is the same oxygen ion which on the other side is bonded to a transition metal ion, which is ionocovalent. So we can actually do a lot with that by tuning the covalency of the transition metal oxygen bond. Now, if we make the transition metal oxygen bond less covalent and more ionic, I will have the electron density more towards the oxygen ion, making an effective negative charge on oxygen ion a little more negative. If I do that, then I make the sodium oxygen bond a little more stronger and shorter. And on the other side, if I have a more covalent transition metal oxygen bond, the electron cloud will be away from the oxygen ion, and I will make the effective negative charge on the oxygen ion less negative, so my sodium oxygen bond will be less strong and long. So why am I saying this? Because, as I said, the starting point of the air-water instability is the sodium ion spontaneously coming out of the lattice. So to suppress that, we want the sodium-oxygen bond to be stronger and shorter if possible. Now we can do that. We can do that by tuning the composition of my transition metal layer. By tuning the composition of my transition metal layer to make the overall electronegativity of the transition metal oxygen slab go down. So to make the transition metal oxygen slab less covalent, the covalency of the transition metal oxygen slab to go down, so that I can have a greater effective negative charge on the oxygen ion, this being a more ionic and less covalent, and I can have a strong sodium oxygen bond. So now how can I do that? If I select a combination of cation combination in my transition metal oxygen slab, which has a lower surface charge density, which means if I lower the charge to size ratio of the cation combination in my transition metal layer, if I have a low charge to size ratio of my cation combination in my transition metal layer, I can have this scenario that my transition metal oxygen slab becomes less covalent, more ionic, and I can have a stronger sodium oxygen bond, and I can suppress the spontaneous sodium removal when exposed to air or maybe even water. So we can see that. Now later we will see that we can use the same concept to develop p-type structure with a higher sodium content. As I said, it's very important to have the p-type structures actually being used. So now to improve the air-water stability, study the effect of variation of charge to size ratio of the cation combination in my transition metal layer. We designed and developed a few model layer transition metal oxide materials. Now what we saw is that when the charge to size ratio in the transition metal layer is lower, I indeed have a narrower interslab spacing, which means my sodium oxygen bond is shorter and hopefully stronger. Now DFT by my colleague and IIT Bombay, Abhijit Chatterjee, so they also showed that when the charge to size ratio in the transition metal layer of the cation in the transition metal layer is lower, the effective negative charge on the oxygen ion is more, which means my sodium oxygen bond will be stronger. Now, so how does that affect the air-water stability? So when I have a very high charge to size ratio in the transition metal layer, the cation combination, I expect it to be very poor in terms of stability, and that is indeed what we see. 15 minutes air exposure, it's totally gone. Lot of surface impurities, and we can see a structural transformation from O3 to P3 due to spontaneous sodium extraction. In just 15 minutes time, it is same even for after just 5 minutes. Now, on the other hand, the one with the lowest charge to size ratio, which we expect to be very much air stable, is indeed so. Even upon air exposure for more than a month's time, there is no change in the XRD. Coming to soaking in water, yes, this high charge to size ratio containing material is extremely unstable when put in water. Just 3 hours is good enough to completely damage the material. But again, this one, the one with the lowest charge to size ratio is water stable even for 12 hours of soaking. That is a very important point. If we look at the TEM, you can see this is totally damaged, whereas this is absolutely intact even after 12 hours of water soaking, as if nothing has happened, as if nothing was done with that. So now when it comes to the electrochemical performance, so the one with the highest charge to size ratio of the cation combination in the transition metal layer, so that there is no electrochemical performance upon being soaked in water for 12 hours. Whereas, and we can see a huge increment in the impedance. Whereas the one with the lowest charge to size ratio, which we found to be water stable, the electrochemistry also proves that. There is no change in the electrochemical behavior even after 12 hours of water soaking. The potential profiles, the capacity as well as the impedance tells exactly that. And the materials with intermediate charge to size ratio follow suit when it comes to the capacity as well as the impedance. There is something more interesting in that, but I don't have much time to go through that right now. So anyway, so this proves that if we lower the charge to size ratio of the cation combination in the transition metal layer, it can make the layer transition metal oxide highly water stable upon soaking even in water. Forget about living in air, it will be stable. Now coming to another thing which we observed, which we were not expecting, that even when it comes to the electrochemical performance of these materials with varying charge to size ratio, even when nothing is exposed to air, synthesized and kept nicely in the glove box, absolutely well protected. but still the ones with the low charge to size ratio performed better than the ones with the high charge to size ratio. And so this was not something which we were expecting. We were just investigating the electrochemical behavior because we have made the materials and let us investigate although. So but we found made an interesting observation. So as the charge to size ratio in the transition metal layer increases, we see the cyclic stability decreases drastically, and it follows a trend. Now when we did the in situ synchrotron XRD, so we found that the ones with the highest charge to size ratio, during the charging and discharging, they undergo all possible structural transformation, and no wonder they are not stable upon charge discharge cycles. So the capacity fades very quickly, whereas the one with the lowest charge to size ratio undergoes only the one reversible the structural transformation O3 to P3 and back. So no wonder that this is very stable. Now when we looked at the DQDV, we found that for the one with the low charge to size ratio, one has to charge it to a higher potential to see the phase transformation, and no wonder it suppresses the other phase transformations as opposed to the ones with the lowest charge to size ratio. Now when we looked at the synchrotron XRDs very carefully, we figured out that there seems to be kind of a critical ratio between the interslab spacing and the slab thickness at which the onset of O3 to P3 phase transformation gets initiated. Now for the materials with lower charge to size ratio, the initial ratio of the interslab spacing to slab thickness is far below that of the critical thickness. So one can pull out lot of sodium before this transformation gets initiated, and so one can suppress the further transformations, as opposed to these where a little bit of sodium extraction will initiate the O3 to P3 first phase transformation, and there will be host of the other phase transformation taking place, making the material absolutely useless over long-term cycling. So this is just one example that it's an earlier example. So now the performance is even better with some other modifications. So it shows that not just air stable or water stable, we could actually make aqueous processed electrode. That is, we did not use NMP PVDF to make the electrode, rather we used water and sodium alginate to make the cathode, and the performance is very similar compared to the NMP processed one. This is up to 200 cycles, this is 750 cycles. Right? So we could actually make aqueous process cathodes with this water stable layer transition metal oxide cathode materials. Now this is another example. I don't have time to go elaborate this, but we can show that the same concept can be used to improve the rate capability. Normally the O3 structured layer transition metal oxides are not as rate capable as the P2, but even the O3 one can improve the rate capability by tuning the charge to size ratio and increasing the sodium interslab spacing. So that one can do. Now coming to another very interesting part and very important part again, that is how to develop high sodium containing P2 structured layer transition metal oxide. Again, as I said, this talk is based on one concept and I will use the same concept. And that is the covalency of the transition metal oxygen slab, and I tune this using the charge to size ratio descriptor. Now for P2 structured layer transition metal oxide, why this is important is, if we look at the coordination, octahedral versus prismatic, in octahedral coordination, the oxygen ions are not directly one on top of the other. They are slightly tilted. Whereas the prismatic coordination, the oxygen ions are right on top of the other. So for prismatic coordination to be stable, we need the effective negative charge on the oxygen ion to be less negative, so that they are okay staying one on top of the other. And how do we do that? Again, going back to the concept of covalency of my transition metal oxygen slab. So now in this case, if I have a greater covalency of my transition metal oxygen slab, I will lower the effective negative charge on my oxygen ion, and I will allow them to stably stay directly one on top of the other and form a stable configuration. In addition to that, a greater covalency of my transition metal oxygen slab also lowers the effective positive charge on my transition metal ion, and that is important because in a prismatic coordination there will be phase sharing between the transition metal ion and the sodium ion. So if my transition metal ion is less positive in terms of effective charge, the repulsion between my transition metal ion and phase sharing sodium ion will also be lower. So overall, if I increase the covalency of the transition metal oxygen slab, I can have more stable P2 structures, even with more and more sodium content, which will bring these two closer. So now when we looked at the literature, we found all the materials reported P2 versus O3 can be separated out in terms of the charge to size ratio and the sodium content. Now using this map is very important, because using this we can actually figure out that if I want a sodium content of say 0.9, which is very difficult, we have tried, not yet, sodium content of 0.9, what is the charge to size ratio that we need to have so that we design the composition of the transition metal layer. But anyway, what we could achieve was a sodium content of 0.84, which is also way beyond the 0.7 per formula unit or 0.67 per formula unit, which are usually obtained for the P2 type structures. And we could achieve a phase pure P2 type structure, and this material, it's now very easy to make it, and the performance is also good. This is a high sodium containing P2 structure layer transition metal oxide, so the performance is very good. Between 2 to 4 volt we get a discharge capacity of close to 150 milliampere hour per gram, and the cyclic stability is excellent. So this is a very good material even from a practical perspective. So it's a full cell, I don't want to talk much about it. And going by our theme, the group's theme, this is also water stable, because due to high sodium content, my interslab spacing is a bit sharp. So the spontaneous desodiation does not take place. Now we are making aqueous process cathodes also using this. So now again, the same concept, I told that I will use the same concept to show a few things. So there is a lot of effort on designing and developing these hybrid layer transition metal oxides, PO3, P2, P3, P2, etc. Now all those can be designed based on this chart again, the size, the charge to size ratio versus the sodium content. Now if we use this, we can design compositions which can form P2, which can form O3, and which can form P2O3, and if we just follow that, we got exactly that when we synthesize this material. So this, yeah, so 3 minutes, yeah, sure, thank you. This concept of covalency of the transition metal oxygen slab and the charge to size ratio can also be used for scientifically developing the hybrid layer transition metal oxide structures. So depending on what we want a biphasic and the sodium content, we have to follow this line and we can get the material. Now again, so this is, I don't want to spend too much time, but this high sodium containing layer transition metal oxide, the important point here was the increased covalency and highly increased covalency of the transition metal oxygen bond. And if we understand a little about the oxygen redox, nobody understands too much of oxygen redox as of now, so it can be quite confusing. But we know that the higher the covalency, the better is the stability, because it suppresses the oxygen-oxygen dimerization, and that is indeed what we see, though there are many surprises in this work, which we are trying to understand. So with this material, when we increase the cutoff to 4.5 volt, invoke a lot of oxygen redox, as one can see here, we still get a fairly good cyclic stability. And also not much increase in the potential hysteresis, not much lowering in the sodium transport kinetics. Okay, so yeah, now it undergoes a P2 to OP4 transformation during charge discharge, and it's reversible. So this shows the proof of oxygen redox, the XPS, and also no oxygen evolution during charge discharge. This was done by Nagafani's group at IISc, so we collaborate with them for the DEMS. And so now oxygen KH has revealed some very, very interesting observation, and which can actually challenge the traditional thought process about ligand metal charge transfer. But again, I need probably more than an hour to discuss this, so I will skip it for today. And in terms of the overall symmetry summary, I hope I've been able to convince you that by tuning the overall covalency of the transition metal oxygen slab in the layer transition metal oxides and using a descriptor of charge to size ratio, one can improve the air water stability to significant extents, improve the rate capability, and develop high sodium containing P2 type layer sodium transition metal oxide cathode materials. With this, let me thank the funding agencies, my collaborators, and the students whose work I've been showing and who have been contributing to the group. So the work I showed today was done mainly by Bachu Shravan Kumar as part of his PhD research. So Shravan is now in MIT pursuing his PhD. The oxygen redox part is being conducted now by Adrija, another PhD student. Brijesh is doing the hybrid P2O3 layer transition metal oxides. Ishita was a former master student who contributed in part. So she's now doing her PhD with Rosa Palasin, and Anagha, who is now in Reliance, also was a former PhD student, contributed a part of this work. So with this, let me thank all of you for listening to me. for more than half an hour perhaps, and my apologies for taking too much time. So Voltainics Energy is a startup which we got registered a few months back. So it focuses on sustainable battery storage. So it's mainly one of my PhD student and a project staff. So they are basically taking the lead. I am an advisor. And one important announcement, so we have the Battery Research Society which got registered again early in the summer last year. And so this year we have the first international conference of the Battery Research Society, and that will be in Bangalore. And the convener is Nagafani from IISc. And so it is December 7 to 9. December 6 will be a workshop. So please do submit abstract and please do register. And we need all support from all of you. And more importantly, please become member of the Battery Research Society. Thank you very much.
Thank you, Dr. Amartya, and then very good talk, and then trying to understand what exactly the structural changes, what happens with the charge discharge, and then based on that you modeled and then developed this O3 and then P2 and then P2 plus O3 type of oxides. And then I could see that one of that O3 hybrid one going up to 180 milliampere hours per gram.
Yeah, that was actually the high sodium P2. That's 200 milliampere hour per gram when we invoke oxygen redox, going to high potential.
So if you could improve that the stability, and then so that's
Correct.
going to be a big
Correct.
change in
Correct.
the sodium ion. So
Absolutely.
you can compete and then overcome with an LFP based lithium ion batteries. Also.
Sure.
So that's what I was talking about, riding the second wave, and then so that you can be on top of it.
I got the point when you were saying that.
Yeah, very good talk, and then let us give him a big hand.
Sure. Thanks everybody, and thanks Dr. Vijay for the comments.